Am I audible? Please unmute and let me know if I'm audible. You can type it in the chat as well. Okay, I'll take that as a yes. Welcome to the week 4 live session of the course NPTEL NOC4 EE-39 titled Fundamentals of Semiconductor Devices. Uh, this course is taught by instructor Professor Digvijay from IIC Bangalore, and I'll be the TA for this session. The schedule for my sessions is every Sunday 3 p.m. to 5 p.m. Let's quickly go through the guidelines. You can raise your hand if you have any query, or you can ask it in the chat window. Please make sure that your microphones are muted when you don't intend to speak. I'll try to make it an interactive session, so I would appreciate your cooperation for the same. Uh, I have said it in the last session as well, so I hope you would carry along a calculator with you. Keep it handy during the session, as we'll be doing some numericals today as well. So also keep pen and paper handy as well. The recording link for the session and the lecture notes will be shared by the NPTEL course team in due course of time. And prerequisites for this session would include the last week's lectures, uh, which cover the following content: the PN junction under equilibrium, PN junction under bias, PN junction generation recombination currents. Okay, so I hope I'm audible thus far. Can any three of you at least confirm that if the voice is audible? Okay. Uh, do you guys have any question regarding the course contents, especially that was taught in last week? Looks like nobody has any question. I'll move on to the first problem for today's session. Okay. So calculate the built-in potential of a silicon diode with both donor and acceptor doping concentrations of 10 to the power 15 cubic centimeter that is maintained at 300 Kelvin. Given intrinsic carrier concentration of 10 to the power 10 cubic centimeter, Boltzmann constant Kb is equal to 1.38 into 10 to the power minus 23 joules per Kelvin. Please let me know what should be the VBI for this question. How should we approach this one? your Na and your Nd, that is equal to 10 to the power 15 per cubic centimeter, right? And it's, maintained at 300 Kelvin, right? So T is equal to 300 Kelvin. Uh, Also, your Ni is given as 10 to the power 10 per cubic centimeter. Boltzmann constant value is 1.38 into 10 to the power minus 23 joules per Kelvin, right? And we need to compute VBI, right? What is VBI? ABT by Q, natural log of Na in d by Ni square. So compute this. You have the formula, you have given quantities. Just let me know what should be the VBI for this question. The first question, uh, we need to compute the built-in potential of the diode. We have been provided donor and accepted doping concentrations. The given temperature is stated to be 300 Kelvin, room temperature. The intrinsic carrier concentration is 10 to the power 10 per cubic centimeter cube, per centimeter cube. And your Boltzmann constant value is also provided. Just plug in the values and let me know what should be the VBI. What is this quantity at room temperature? KT by Q. What is this quantity at 300 Kelvin?
0.026 electron volt.
0.026, not electron volt. Since we have Q here as well, right? It will be 0.026. So your VBI would be 0.026 times the natural log of Na and D. Taking the product, this would be 10 to the power 30 whole divided by Ni square would be 10 to the power 20. Just plug in the values and let me know what VBI comes about as.
Zero point two six.
0.26. Can somebody recheck it? Zero point zero two six times natural log of 10 to the power 10. Wait, did I mistake. Somebody just compute this term again. Use K value as this, P as this, and Q you know, right? 1.6 into 10 to the power minus 3. This comes about as 0.026, right? Just recheck it on calculator once. You said uh, 0.26. I guess you took the base as 10, right? But the base is E, right? The base is E. So, yeah, Pranav answered it rightly. This answer is 0.6. What you can do for this is it's to convert this base, there is factor 2.323, if I'm not wrong. Then you can write this as this, right? Which would be 0.026 into 2.303 times 10. And this should be 0.6 volts. Just let me know if I commit any mistake. Okay, so your VBI is what? Your VBI is 0.6 volts, right? And uh, uh, yeah, that's pretty much the question. Okay, let's move ahead. Is this question clear? This was just based on calculations, right? So I'll skip this one now. Let's move on to the second one. Now you need to calculate the depletion width for a step doping of silicon that is operated at 300 Kelvin. Your accepted dopant concentration is 10 to the power 17 per centimeter cube, and your donor dopant concentration is 10 to the power 14 per centimeter cube. Okay, and you can take the intrinsic carrier concentration of 10 to the power 10 per centimeter cube. The Boltzmann constant is given. Now just compute the depletion rate. See, for a given PN junction, we have, as we saw in the last question, your VBI is KT by Q log to the base C NA by NI square, right? And what is XN? The depletion width on the inside of the junction. Your XN is 2 epsilon S epsilon naught by Q, and you have this factor NA ND NA plus ND, right? And VPI. and there's a square root. Now, this is xn, right? What about xp? You also know xpna is equal to xnnd, right? This comes from the charge balance, right? And you can use this equation to compute xp, because then xp is just nd by na times xn. Once you obtain this, you can find xp, right? So, uh, so I should write that as well. This would give your xp would be nd by na times xn, right? And what would your depletion width be equal to? What's W in terms of this and this? Sorry, this and this. The W is total depletion width, right? Xn is the depletion width on the inside of the junction. Xp is the depletion width on the P side of the junction. So what should be W?
xn plus xv.
Xn plus X. Correct. So now you have all the quantities, right? Firstly, you will obtain VBI, substitute that VBI here, obtain Xn. Once you get Xn, use this formula to compute XP, and then take the sum of the two and compute W. Also, tell me one thing. Your acceptor dopant concentration is 10 to the power 17. The donor dopant concentration is 10 to the power 14. Right? So, I mean, there is a difference of three orders, right? So, what do you expect? How XP and XN uh, should have relative magnitudes? Would one, I mean, be very large than the other? Would they be comparable or what? Come again. See, in the question it's given, your Na is very, very greater than Nd. So what can we say about Xp and Xn? What should I put here? Hint is to use this charge balance. No matter what doping concentrations you use, this should be maintained, right? So
xp less than xn.
Xp should be less than Xn, right? Yeah, it's correct, right? And then what about this? So what should my W be approximately equal to? Xn, right? I can ignore Xp when I take this sum. So my W is Xn plus Xp, which is equal to Xn. So all you need to do is to compute this. First, you need to compute VBI. First, tell me what is the value of VBI that you will obtain, and then we'll plug that here. Just saw how we computed VBI in the last question. So what is the VBI here? Use a calculator and tell me the value. 1.257 volt. Um, I'll just write the value that I got. Just recheck it, okay? The value that I got is 0.656 volt. Okay. And okay, this is the VBI. What else? Uh, and now use this VBI. Okay. And tell me what's X in. Others may recheck this value. Those who answered can plug this value here. What will be the Q value? Okay, Q would be this, right? Okay, let me write Q. Q would be 1.610 to the power minus 19 coulomb. This is and it's electronic charge Q. In some texts, this Q is also denoted by E. Can someone do this now? Is someone doing this calculation or should I do it myself or answer it? Okay, okay. I'll wait. These values you know, right? For this epsilon s, this would be uh, dielectric constant of silicon, which you can take as 11.7. And for epsilon naught, this is relative permittivity of the free space. You can take this as 8.85 into 10 to the power. Uh, Take farad per meter, I guess. 8.85 into 10 to the power minus 12. Keep it in SI and then we'll see. Oh no, don't keep it in SI since we have per centimeter cube. I mean, this is in CGS. So, okay, the value of epsilon naught that you'll use is 8.85 into 10 to the power minus 14 farad per centimeter. This would take care of the units. And your epsilon s would be 11.7, the dielectric constant of silicon. Now, Q, these, VBI, I gave you. I mean, if anyone wants to compute it, can by just using this formula. Compute this quantity, take the square root, and let me know what is exact. Uh, do you guys have calculator with you, or are you just computing without calculator? Because if you had calculator, this wouldn't have taken much time. I guess that's the answer it myself. You guys can try it at your end as well, or recheck it later. Your xn value is your xn is equal to 2.93 micrometer. And I mean, you can also compute xp, although that would be negligible compute xn. Your xp comes about as 2.93 into 10 to the power minus 7 centimeter, right? So that also tells you that your xn is very, very greater than xp, and your w would be equal to 2.93 micrometer. Fine. Uh, those of you that don't have calculator with you, raise your hands. I mean, there is a raise option, right? That would let me know how many don't have calculators. Does everyone have a calculator then? Since nobody raised hand. Okay, so you guys all have calculator. Then why is it taking much time for these calculations? To verify it, okay? So this finishes our second problem. Now let's move on to the third one. Now choose a statement that most appropriately describes low level injection. In low level injection, your concentration of the excess minority carriers, it is large enough to modify the minority carriers, but it's very small uh, to modify the concentration of the majority carriers. Okay, that is the reason your option one is correct for this one. We'll move on to the next one. What about this? Your PN junction has a contact potential of 0.5 volt. You are having a depletion width of 2 micrometer at equilibrium. Then the forward voltage at which the width, the depletion width, reduces to zero point 0.4 micrometer is. What is the formula for the depletion width? Let me write that down. See here, depletion width under unbiased condition, right? Under unbiased condition, your depletion width would be W, that is equal to square root of F2 epsilon by Q, right? NA plus ND by NAND. And then you have VBI minus VF. Okay. Now, for the constant doping concentration, um, assuming that doping concentration doesn't change, your width, I mean, we can treat this much as a constant, right? So your width is proportional to the square root of your VBI minus VF, right? Now, what about W1 then? W1 is equal to, what is W1? Your W1 is depletion width uh, under unbiased conditions, right? When you're not applying any bias. What is that W1 equal to? It's mentioned in the question. I'm asking to just ensure that of you are attentive. What is this unbiased depletion width? 2 micrometer. Right. So this is equal to, you can write this as K square root of, what should I write? Square root of, your VBI is 0.5, right? Minus, what should I subtract from VBI? Note that this is depletion width under unbiased condition, right? So what is the bias then? How much is VA? Simple question. 0, correct. So I won't subtract anything, right? So this is your W1, and as uh, Jean Roderick mentioned, it's equal to 2 micrometer, right? Now what about this, the second case, right? Our second case is a depletion width under a forward voltage that is unknown. I mean, we don't know what the forward voltage is, but we do know how much this width reduces to, right? Your W2 is K square root of. Your VBI would be same, right? That won't change. Contact potential won't be changing. So this is 0.5 minus, let's keep this VF. How much is this equal to from the question? It's mentioned in the question. I'm expecting answers from others as well. 0.4 micrometer, correct. Now, what about W1 by W2? How much is that equal to? W1 by W2 is square root of zero point 0.5 by zero point 0.5 minus P, right? And this is equal to 2 by zero point 0.4, right? Which is equal to, how much is 2 by zero point 0.4? 5, right? So Your 5 is equal to square root of 0.5 by 0.5 minus VF. Now what? How much is your VF? If you take the square on both sides, you'll end up at this equation. 25 is equal to 0.5 by 0.5 minus VF, right? And just work it out and let me know what is the value of VF. I mean, solve it for VF and let me know what is the VF that satisfies this equation. Zero 0.48, correct. So this is correct answer. So the correct answer is 0.48 volts. Only one student is answering questions. I'm expecting others to chip in as well. Done. Now let's see this problem 5 now. So in the given circuit, your average voltage across a 2 ohm resistor, right? Uh, you need to find that average voltage. Okay, this average voltage. You can consider the following. That your diode has a forward voltage drop of 0.7 volts. The parasitics are negligible. Parasitics are negligible, and your frequency of the input signal is 50 hertz. If you're neglecting parasitics and your operating frequency is 50 hertz, what should be the average voltage across the 2 ohm resistor? Your input AC source is this. If the diode has a forward voltage drop of 0.7 volts, and I'm applying this input source, right? Tell me, when will the diode turn on? When does it turn on? When applied voltage exceeds, not breakdown, yeah, this forward voltage drop, right? So when your applied voltage is exceeding your forward voltage drop, that is the voltage values for which your diode will turn on. And when the diode will turn on, there would be voltage applied across this 2 ohm resistor. And for the values of the voltage that are less than 0.7 volt, the diode will turn off, right? I mean, it would be just an open circuit. Uh, and the voltage that's showing up across this 2 ohm resistor would be, I mean, zero, right? Because no current would be flowing at that time. So now let's do the calculations. Let me write this as well so that you guys. Your diode turns on when voltage crosses 0.7 volts. Right. And it turns off voltage goes below 0.7 volts. Yeah. So that is turning point. And now let's draw the input wave. This is V input. This is 0. This is pi. And this is 2 pi. Now, how much is this? 10, right? This is 10. And there would be a voltage level somewhere around here. Not drawing it to the scale. And this would be your zero point 0.7. Okay. Why I drew this line is because voltage values beyond this line would make the diode as short circuit, right? The diode would turn on and the voltage would be applied across your 2 ohm resistor here, right? So let's draw V out because that is of more interest. And this is V out. Omega T, right? Right. Your output waveform would exist only between these two time intervals. Let me name them. If this is TA and this is TB, your output waveform can only be between TA and TB. Would be a scaled version of the input, right? Would be a scaled version of V input and put this shape, right? So this is the region for which the diode would turn on, right? Now what about TA? What is TA equal to? Now I want answers for this one. See, let's zoom it. This much is what? Zero point 0.7, right? This much is TA, right? So what can you say about uh, just a second. What is the equation that we have? Okay, 10 sine of omega t, right? We write it here. Our V input was 10 sine of omega t. Now your V input is at TA, right? Let me write this now at TA. At TA, your V input was 0.7, right? That's how we define this TA. This is corresponding to the voltage level of 0.7 VI. I mean, at least the amplitude is 0.5 at this point. So I can write 0.7 is 10 times sine of omega TA, right? And uh, okay, wait. This is not, I should replace this whole by TA. Why? Because this is omega t axis, right? And I'm writing this as omega, I mean, this is omega t is equals to TA, right? That's why I should replace this whole omega t by TA. Now answer me, what should be the value of this t? How much should this be? Your TA would be sine inverse of 0.7 by 10. Uh, I mean, that you can see what the value would be and just keeping this in terms of sine, right? This would be sine inverse of 0.7 by 10. Now we will see why I'm keeping this in this form. This would help us later onwards. Similarly, you can see why TB would be pi minus sine inverse of 0.7 by 10. Okay, convince yourself that this TB is equal to this. And your TB, which is this, would be equal to this much minus this much. Sorry, this much pi minus this distance. So this distance we can compute in this fashion. I mean, this is also symmetrical from the symmetry of the problem. That's why I can write TB as pi minus TA, right? This and this would be equidistant, right? This is sinusoidal symmetrical curve. So this zero point 0.7 is here, zero point 0.7 is here, and this distance would be equal to this. So that's why I can write it as pi minus sine inverse of 0.7 by 10. Is this clear? Please answer yes if this makes sense. Okay. So now what about the average value of V out? Because that is of interest, right? We have to compute this average value, right? And we'll proceed as follows now. Your V out is equal to, sorry, your V out average, I should write. Right, that is equal to 1 over 2 pi TA to TB, and this would be, I mean, this is uh, clipped by zero point 0.7, sorry. This is clipped by zero point 0.7. So this value would be 9.3, right? 10 minus 0.7, that is 9.3. So this would be 9.3 sine of omega t d omega t, right? We'll take the average of this. Hope this is clear why I took the limits of integration from TA to TB, because we discussed in detail how diode switches on and switches off at these time instances. Now, okay, this would be 9.3 whole divided by 2 pi. This is cos of omega t, and the limits are TB to TA, right? And then you have 9.3 by 2 pi.
Sir,
Yeah,
how it comes to 9.3?
9.3. The reason why I wrote this because zero point 0.5 is the forward voltage drop in the diode, right? So a zero point 0.7 voltage drop goes in the diode, and you are left with this 10 mines of that, right? Well, how you can imagine this is you can replace diode by uh, a battery, right? A cell, a battery, or a potential source, DC source, right? Uh, that opposes this, right? So can replace this for voltage that are greater than zero point 0.7. Can replace this by this. Is this clear now?
Yes, sir.
Okay, but you can only replace this by uh, this DC source only for the voltage that are greater than zero point 0.7, right? Because for voltage that are less than zero point 0.7, your diode won't turn on, right? So this would effectively be an open circuit. Hope this is clear. So that's why I wrote 9.3 here. Now, uh, okay, just perform the integration. I mean, we just need to put in the values, right? Your TA, what is TA? Your TA is sine inverse of, right? This is your TA. Your TA is sine inverse of what? Zero point 0.7 by 10. Similarly, uh, your TB, right? Your TB would be pi minus this quantity. Fine. And uh, now it's matter of plugging in the values. This comes about as follows: 9.3 by 2.2 pi, sorry, cos of sine inverse of zero point 0.7 by 10. Right. This is what the value you'll get. So how much is this? Can anyone tell me? the answer corresponding to this. Take it in radians. I mean, take this in radians and tell me. So the V out average that you'll get is 2.953 volts. And this is V out average that you'll obtain. So the average voltage across the 2 ohm resistor is 2.953 volts. Now you also know, I mean, how we reached this point. Fine. Now let's move on to the next problem. Attempt this problem. Now your dopant concentration for this problem varies as follows. It varies as your n of x is equals to n0 exponential of minus ax, right? And what uh, okay. So your n-doped semiconductor is having a dopant concentration that varies as this, and it's used to form a metal semiconductor Schottky contact. Your junction of the metal semiconductor contact is located at x equal to 0. Fine. And your depletion region extends up to x equal to 2 by a in the semiconductor. So your depletion region, right? XD is 2 by a. Now the semiconductor has a permittivity of ES, epsilon s, and given that Q is the magnitude of the charge of an electron and assuming full depletion approximation, magnitude of the built-in potential is best expressed as this expression, right? A times Q and naught by A square epsilon s. And you need to find the value of A. So let me show you how. I mean, I'll just give you the recipe for this question and you'll work it out yourselves. What is VBI? Wait. Actually, I'll skip this question, right? Reason being, this is from metal semiconductor junctions, right? And I don't think that was taught. Was metal semiconductor junctions taught? No, right? We just taught PN junction, PN diodes. That was the content, right? Was not yet teach. Yeah, I mean, it won't make any sense if I start this because it would unnecessarily create doubts. So we'll move this page to the trash. Done with this. Okay, let me first see if you guys can solve this one. Yeah, this one you can solve, right? This one is easy. So this would be the last question for today as well. So I would request everyone to answer questions as much as possible, whatever I'll ask. So now a semiconductor has an intrinsic area concentration of 10 to the power 10 per cubic centimeter. Your hole mobility is 400 centimeters square per volt second. The carrier mobilities, they remain unaffected by doping. A PN junction diode with a cross-section area of 10 to the power minus 6 centimeters square is constructed with this semiconductor, such that your P and N side both have dopant concentrations of 10 to the power 14 per centimeter cube. It is known that your minority carrier lifetime of electrons in holes is same, and it's equal to 10 to the power minus 6 seconds, right? 1 microsecond. Your thermal voltage is exactly 25 millivolt, right? If a forward bias voltage of zero point 0.5 volt is applied, uh, what is the current flowing through the diode? Okay, I'll help you out, and then you'll proceed to solve this on your own. So your Ni is 10 to the power 10 per centimeter cube, obviously. Your whole mobility is 400 uh, centimeter square per volt second. What else is given? Yeah, your NA RNA and NT. Your Na and Nd both are 10 to the power 14 per centimeter cube, right? And your tau n is equal to tau p is equal to 10 to the power minus 6 seconds, right? Now, what about Vt now? Vt would be equal to Kt by Q, and that would be equal to 25 millivolt, right? Yeah. Vt would be 25 millivolt, and your Va would be this. Va is your forward bias voltage that's applied. Your Va would be equal to 0.5 volt. And I have been asked to find J. Your J is Js exponential of QVA by KT minus 1, and that is equal to Js exponential of 0.5 by 25 to the power minus 3, right, minus 1. So your J would be Js times 4.85 into 10 to the power 8, right? Your wait, okay. So your Js is, I mean, you can compute V by tau p raised by 1 by 2, 1 by nd plus your mu n by tau n raised power 1 by 2, 1 by na. If we'll uh, compute it, your Js would be I mean, all the quantities are given, right, in the question. And can obtain Js as 130.50 times 10 to the power minus 11, obviously, ampere per centimeter square. That is your Js, right? And uh, what is in J? J you can obtain from this then, right? Just multiply this by this. So your J would be 0.631 ampere per centimeter square. What about I? That is J times A. Therefore, your I is 0.631 10 to the power minus 6 ampere, right? 0.631 microamps. That is your I. Wait, it was A. Okay, this was your A, right? Cross sectional area was 10 to the power minus 6 centimeters square. Is it fine? I mean, that was the current that we had to obtain. We obtained that. Now, homework would be to do the relevant problems from, again, the book Semiconductor Device Fundamentals by Robert Perry. I mean, there are, uh, I mean, do the problems from first couple of chapters of PN diode section, right? I'm not sure what is the chapter number, but there are probably four chapters on dedicated to PN junction diode. Do the problems from first two chapters. Yeah, that's it from my side. If you have any questions, you can let me know. Otherwise, we'll call it a day. Any questions? No. Okay.
Sir, would you please repeat again class question number 8, sir?
Just a second. You mean this one? This one?
Yes,
Should I
sir.
repeat this? Okay. So we were provided, I mean, Ni was given, right? Whole mobility, electron mobilities, and other quantities were provided. What we had to compute was the current through the diode. Okay. So your current through the diode, I mean, in terms of current density, I mean, there are multiple ways of approaching this problem. You can uh, go ahead and use your uh, notation symbols and formulas that you have gone through the course. I did it in one of those ways, right? Your J is Js exponential of QVA by KT minus 1, where your J is the current density in the diode, right? And this is Js is your reverse saturation current density. And there is an expression for this Js. What I did was I plugged the values. I mean, I used Ni, I used, see, your T was is provided. Okay, thermal voltage is 25 millivolts. So, uh, I mean, your KT would be 25 milli electron volt, right? And I also used mu P, mu N, tau P, tau N, ND, NA, NA and ND were 10 to the power 14% meter cube. Tau N and tau P were 1 microsecond. When I plugged those values, I got this number, right? Your Js reverse saturation current density came about as 130.50 times 10 to the power minus 11 ampere, right? So your what your J would be this, right? Because the value of this factor is 4.85 into 10 to the power 8. So when I multiplied that, I obtained J, right? And obviously, since this is current density, it will have units of ampere per centimeter square. And when you will multiply this by the cross-sectional area in units of centimeter square, you'll obtain current in amperes. And this is the area that was provided. Cross-sectional area was 10 to the power minus 6 centimeter square. And when I multiplied this with J, I got this value. Right here, I was 0.631 microamps. Is this clear now? Uh, I'm
Yes,
asking to
sir.
the
Yes,
student.
sir.
Okay, okay, okay. Thank you. So does anyone else that's having any question or any query? No questions? If that's the case, I'll stop the meeting. Thank you. Guys can leave.